In today's lecture, we are going to start with surface integrals. So the aim is that if I have given a function on a surface, for example, let us say I look at the sphere, which we can believe is a surface. I will come to the rigorous definition of surface later. Suppose I have a function defined on a sphere, how to integrate the function over a sphere. Okay. So first let us start with definitions of surfaces. What do we exactly mean by surfaces? Well, most of the surfaces which we encounter will can occur as graphs of some functions like the function f from R2 to R, let us look at, and then let us look at the set z equals to f of xy, where xy belongs to R2. What we mean by this? We actually mean this subset of R3, that is x, y, fxy, where xy is in R2. Well, this is just the graph of the function f, which is defined from R2 to R. Similarly, if I come down to dimension 2, if I look at some equations of curves, they are also given sometime, not always, by graphs of certain functions f from R to R. Suppose I have a function f from R to R, then if I look at this set x f x, then you already know that this is a curve where x in R, this is a curve. Similarly, if I look at this kind of a set where f is a function from R2 to R, this is a surface. These are certain examples of surfaces. We will see later that all surfaces are actually not given by graphs. So we will generalize the definition also. Well, another definition of curve we have given as some maps C from closed interval AB to R2. Okay. So CT written as XTYT, this was a curve. Okay. This is also a curve. So we can have an analogous definition to this for surfaces also. Well, that is given as follows, that suppose A is a subset of R2. Suppose I have a map phi from A to R3. We will assume phi is differentiable function. So the domain A is such that the derivative of phi makes sense. Then this phi actually determines a surface. And it is given by S. What is the set? The set is x uv, comma y uv, comma z uv, where uv belongs to A. Okay. So it essentially means that on surfaces you have essentially have 2 degrees of freedom, u and v. When for curves there is only 1 degrees of freedom, that is t. Okay. And what do I mean by x, y and z? Well, phi is a function from A to R3. So the image of phi will have a x coordinate, it will have a y coordinate and a z coordinate. Those coordinates I have written as x uv, y uv, z uv, because these coordinates are going to be functions of u and v. Now this is the most general kind of surfaces we are going to deal with. These are called parametric surfaces. And u, v these are called parameters. Now another kind of surface we will deal with sometime is the level set of a function. So this is the most general kind of definition which I have. Third is a level set. Suppose I have a function f from R3 to R. I will assume a technical condition whose role is very difficult to explain at this point of time. Just assume this condition. The condition is that gradient of f is not equal to 0 for all points. Okay. Then I look at this set. I fix a constant c in R and I look at this set S, that is all x, y, z, such that f of x, y, z is equals to c. Okay. Now why this is a surface? The way to imagine that this is a surface is that suppose x and y is given to you. Then from the rule f x, y, z equals to c, anyway I will be knowing the definition of f, I can actually find out what is z, right? For example, let us take the function I take a very simple function f from R3 to R given by f of x, y, z. Let us say it is equals to x plus y plus z. Okay. If that is the case, let me take c to be equals to 1. Then my surface S is all x, y, z such that f of x, y, z is equals to 1. That is all x, y, z such that x plus y plus z equals to 1. Now once I know x and y, I can calculate z from this equation, and you know what exactly this equation represents. It represents a plane. Okay. So that is a surface. Now let us look at some more examples. I look at the sphere S, that is all x, y, z, such that x square plus y square plus z square equals to r square. So it is a sphere of radius r. Now you can imagine that this sphere must be a surface, because if you stand on the sphere, then it is kind of a two-dimensional thing, right? You can have only 2 degrees of freedom there. But how do we rigorously explain that S is a sphere? Well, for S, what I want to do is I want to show that this is a parametric surface. That means I have to find 2 parameters by which the sphere can be determined. Okay? So let us try to draw the sphere first, from that it will be clear. Okay? So this is my sphere. So question is, how do I express any point on the sphere as a function of 2 parameters? Okay? If I can do it in a nice way, that will show that S is a surface represented by 2 parameters. Okay? So let us take a point P here. This is my origin. This is the point P. Well, now I want to find the coordinates of this point P in terms of 2 parameters. Now if I want to find the coordinates, I want the height, length and breadth. Okay. So this is the point P on the sphere. There are distances which I want to find. One is this distance, other is this distance. okay, and the total height. Now what I do is I join the point P by a line with the origin. Then since the sphere has radius r, I know this line OP, length of OP is equals to r. That much I know. Well, now suppose I look at this angle. I call this angle phi. And then I have to use some other angle. Well, let us draw this line. Okay. Let us say this angle here is theta. Okay. So I have used two angles. Now these two angles are parameters. Using these two angles, I should be able to represent the point P in 3 coordinates. Well, question is, what should be the x coordinate of P? Now let me give some names. This point is A. Let us say this point is B. Okay. First, what I want to know is what is OA, that is this length. For that, first I try to find what is OB. That is easy to find. OB, if you understand which angles I am looking at, OB is nothing but R cosine of pi by 2 minus phi. Okay. Phi is the angle which the line OP makes with the z axis. This is my z axis, this is x axis, and then here is my y axis. Okay. So I have found out what is OB. Well, what is r cos pi by 2 minus phi? This is nothing but r sin phi. Okay. Then what is OA? OA is nothing but OB cos theta. That means r sin phi cos theta. So I found out what is OA, that is the x coordinate of P. So once again, what I am doing is, I know the length of OP which I have drawn here, that is r. Now I want to find what is OA. OA is going to be the x coordinate of the point P. Now to find OA, what I do is, I first find what is OB. Now since phi is the angle between OP and the z axis, OB turns out to be r cosine pi by 2 minus phi, which is r sin phi. Using that I can find what is OA. OA is precisely r sin phi cos theta. Okay. So OA has been found out. Next, I want to find what is the y coordinate of the point. Okay. That means I want to find what is AB. AB will give me the y coordinate of the point P. Now let us look at the triangle. What I have here, this angle between OA and AB is pi by 2, and the opposite angle is given by theta. So AB, that is nothing but OB sin theta. But I know what is OB. OB is r sin phi. So AB is r sin phi sin theta. Okay. Next thing remains is what is the height. That is, I want to find what is OP. OP is the height, that is the z axis, z coordinate of the point P, which is easy to calculate. The z coordinate OP, well, usually by OP I was meaning the line joining O and P. Here what I mean is, well, let me call this point Q, that is the projection of the point P, and then what I want to know is what is OQ. Well, OQ is then nothing but r cosine phi. Okay. So what are all the 3 coordinates of the point P? The x, y, z coordinate of the point P, that I can easily calculate now. the coordinates are turning out to be, first the x coordinate, that is r sin phi cos theta, then the y coordinate, that is r sin phi sin theta, and then the z coordinate, that is r cos phi. Okay. So what exactly is the map now? Now let us see first what is the variation of phi and theta. Now if you want to get any point P, the point is either on the upper hemisphere or it is on the lower hemisphere. Okay. In any case, if it is in the upper hemisphere, then the phi, variation of phi can be from 0 to pi by 2. That is very clear. And if it is on the lower hemisphere, then the variation of the parameter phi is from pi by 2 to pi. So as a whole, my phi varies from 0 to pi. And what about theta? Theta is actually measuring the angle between the x-axis and the point, okay? But it can have a full round. That means this theta, it can vary from 0 to 2 pi, okay? So finally, I get the map. The map is that I look at the map. Let us call it R, little r. It is a map from 0 pi cross 0 to 2 pi, okay, to the sphere S, that r of phi theta, that is, now comes the first coordinate. I go back to the picture again. If I look at the first coordinate, that is r sin phi cos theta. So this is r sin phi cos theta, then r sin phi sin theta, and then r cos phi. Notice here that the capital R which I am writing, it denotes the radius of the sphere. Okay, so it's not varying. So the only variations which we are having here are phi and theta. So you can see that any point of the sphere now have these coordinates. These are called the spherical polar coordinates. In that, the only variations which can happen are in phi and theta. So using those two parameters, I could represent the sphere S. So it's a surface, and this is the parametric equation of the sphere of radius r. Okay. Now, after understanding the basics of surfaces, let us go to the tangent spaces. That is one concept we will be needing. You already know it, so I will just recall it and try to be very short. So suppose I have a parametric representation of a surface S. So S equals to phi uv, where uv belongs to some subset of R2. I want to find, since I am concentrating on the surfaces, I want to find the tangent plane of S at a point, let us say u0, v0. Okay. So what is the idea? What you do is you first fix v0, okay, and then look at this quantity phi u, u0, v0. Okay. This gives you a direction of the tangent to the surface at the point u0, v0, and the orthogonal direction actually can be found then by phi v u0, v0. So what you do is, in the equation of phi, you first fix v0, then it becomes a curve, okay. Then you take the tangent of that curve, find the tangent line. You need the direction of the tangent line only. In the next case, what you do is you fix u0 and find the, look at the curve phi of u0 v and find the direction of the tangent line. It gives you two orthogonal directions, okay. And then you look at n, that is phi u cross phi v, okay. then this is normal to the surface. Okay, and then the equation of the tangent plane, if let us say phi u naught v naught is equals to x naught y naught z naught, then the equation of tangent plane is nothing but n dot x minus x naught, y minus y naught, z minus z naught equals to 0. Okay. So, this is the equation of the tangent plane of a surface S at a point x naught, y naught, z naught. Now, I want to give two examples where these constructions will be even more clear. Now, the first example, let us look at the surface S, which is graph of a function f. Certainly, I will assume that f is a differentiable function, otherwise I cannot work with it. So, let us take a point x naught, y naught, f x naught, y naught. At this point, I want to find the graph of the function, graph of the tangent plane of the surface. So, what is the surface S? S is nothing but x, y, f x y, where x y belongs to the domain of the function. Okay. Now, that means what is my parametric representation of the surface? It is given by this function, that phi of u v is equals to u v f u v. This is the parametric representation of the surface. That means given any graph of a function, I already get the parametric representation of the surface, and the precise parametric function is phi. Phi of u v is u v f u v. So, I first calculate phi u. So, that turns out to be then I plus f u at u naught v naught k. I am just differentiating term by term. The first term u, if I differentiate, I get 1, v is 0, f produces the partial derivative. In the vector notation, if I use I j k, what I get I have written here. Now, if I look at phi v, of course, it means at u naught v naught, what I get is j plus f v u naught v naught k. Okay. Now, I can calculate what is phi u cross phi v. So, I will do the calculation here. I write it as I j k, then 1 0 f u, then 0 1 f v, just to calculate, and this is 0. So, what do I get? What I get is minus f u u naught v naught I, then j, with j what I get is minus f v minus f v u naught v naught j plus k. Okay. So, then the equation of the tangent plane is easy to calculate. So, equation of the tangent plane in x minus x naught, y minus y naught, z minus z naught dot, I need to know the normal vector, that is given by this. This is a normal vector. So, I just use that, this is Fu if I do the dot product, what I get is that z minus z naught okay. So this is the equation of the tangent plane, that is all those x, y, z. So the equation of the tangent plane is x, y, z. If I call this equation 1 such that x, y, z satisfies 1. This is the equation of the tangent planes of the surface at the point x naught, y naught, z naught. Now let us look at another example. Suppose I take the upper hemisphere of the sphere x square plus y square plus z square equals to 1. Okay. So I want to calculate the equation of the tangent plane to the sphere at the point 0, 0, 1. Okay. Before applying the formula, let us see what it means. So I draw the sphere here. I draw the upper hemisphere actually. This is the upper hemisphere. This is the point 0, 0, 1. We can very easily visualize what exactly is the tangent plane there. You just put a postcard on the top. That is this plane. This should be the tangent plane to the sphere at the point 0, 0, 1, because the plane is tangential to the sphere, and the equation of this plane is, I know what it is just z equals to 1. Z equals to 1 is the plane parallel to the xy plane at the height 1. That looks like the tangent plane. Now I have to see whether it follows from the formula which I have derived. So for that, what I do first is that I visualize this upper hemisphere as the graph of a function. So which function I am looking at? Well, I look at the function f of xy is square root of 1 minus x square minus y square. I am taking the positive square root. And then x, y, fxy, this is a sphere, upper hemisphere. This is my surface S. Okay. Now if I want to calculate the tangent plane at 0, 0, 1, I can use my previous formula. For that, what I will need are fx. That turns out to be minus x by square root of 1 minus x square minus y square. I will also need fy, that is minus y by square root of. But note that I will need fx at the point where I want to find the tangent plane, that is 0, 0, 1. If I put x equal to 0, then fx turns out to be equal to 0, so is fy. Then the previous formula of the equation of a tangent plane at a point x naught, y naught suggests that I get z minus z naught, which is 1, that is equals to x minus x naught into fx at 0, 0, 1 plus y minus y naught into fy at 0, 0, 1. But fx and fy are 0, so what I get is 0. This implies the equation of the tangent plane is xyz such that z is equals to 1. But this is precisely the plane which I have drawn here. This is the plane z equals to 1. So it matches with our intuition. Now, with these ideas, now I am going to move towards the surface area, which will be virtually used in doing surface integrals. So we start with the surface now to calculate the surface area, which is a graph of a function. So let us say I have a function f from R2 to R, differentiable, and I look at the surface S, that is x, y, fxy. And I also know that this gives me the parametric representation of the surface also. So call that function phi. So phi of xy then is x, y, fxy. So pictorially it would mean, suppose this is the domain and then the surface it looks something like this. This is the surface and there is the map phi, which is given in terms of f, because I am dealing with surfaces which are graphs of functions. Now what I do is I start with very small rectangles here. Okay, the way I am drawing it, it doesn't look very small, but what I mean is a small rectangle. Okay, and then I level the coordinates. Say this is xy, that is one edge of the rectangle. Then this one has an infinitesimal increment in the x direction. So I write this x plus dx y, and then this fellow at the top is x y plus dy, and the last one, that is x plus dx then y plus dy. Now this small rectangle under the map phi is mapped, let us say, to a curved rectangle. Okay, it goes to something like this. Let us say this is the point P1, P2, P3, P4. So what is P1? P1 is nothing but x, y, fxy. Okay. Then what is P2? P2 is x plus dx, y, f of x plus dx, y. Now what I am going to use is the following, that if I look at f of x plus h, y minus f of xy, I say this is approximately equal to fx at xy times h. That is the linearization of this curve. Now if I use this, then this P2 turns out to be equal to x plus dx, y, then fx at xy dx. Now I am going to use the fact that f of x plus hy minus fxy is approximately equal to fxxy h, where fxxy stands for the partial derivative. So I am using the linearization of the curve. Okay. Now if I use this, then I can actually write that P2 x plus dx y fxy plus fx xy dx. Let us look at what is P3. P3 was x y plus dy, then f of x y plus dy, which I say is approximately equal to x y plus dy. Again I want to use the partial derivative with respect to y of f, okay. This is fxy plus fy at xy dy. Then comes P4, which is x plus dx y plus dy f of x plus dx y plus dy, which is approximately equal to x plus dx y plus dy fxy plus fx at xy dx plus fy at xy dy. Okay. So now I got a genuine rectangle with this as the sides P1, P2, P3, P4. Then what is the area of that rectangle? If I call that ds, then ds is nothing but norm of the vector P1, P2 cross product P1, P3. Okay. And then I am going to sum over all these rectangles to get the area of the surface. That is the idea. So here the only idea involved is to find the area of the curved rectangle ds, but it is so small that I am approximating it by the linearization of the bounding curves, which I am doing using the partial derivatives. Now what is P1, P2 in question? Well, P1, P2, if I write down, that is dx 0 fx at xy dx. It is just P2 minus P1. And then P1, P3, that is 0 dy fy at xy dy. Okay. And then ds I can calculate. I just write it as this I j k dx 0. I will simply write fx here, but what I mean is fx at xy, then 0 dy fy, I have dx here and I have dy here. Then the norm of this vector, because after all area is going to be a number. Now what is the norm of this vector? It is the norm of the vector minus fx dx dy, comma, then fy dx dy, then just dx dy. Let us see whether all the calculations are correct here. Then I times 0 into this minus dy into this, so minus fx dx dy, then j into this minus, so yeah, so here is a minus sign here. So this is what I get. Then this norm is easy to calculate. This is square root of 1 plus fx at xy square plus fy at xy square dx dy. okay. And then the total area of the surface, if I call it AS, that is, I just going to sum up all these rectangles over the space of parameters, which is domain of F. So, domain of F square root of 1 plus fx at xy square plus fy at xy square dx dy. Okay, this is the total area of the surface. Now, when I go to the genuine parametric representation of a surface, that is, it is not given by a curve, I can do the analogous, absolutely analogous analysis there, and in that case what I get is as follows. So, I have a map now phi, so it is a parametric surface. So, S equals to phi uv, where uv belongs to some set D. Suppose this is the surface, I want to find the surface area of this surface. Again I start with some infinitesimal rectangles which looks like this. The points are uv, u plus du v, then u, v plus dv, then u plus du, v plus dv. Okay. This goes by phi to a curved surface, goes to a curved rectangle. So, the points are phi uv, phi u plus du v, phi u plus du v plus dv, then phi u v plus dv. Okay. Once I do this, then again I can linearize by now phi u and phi v. So, it turns out then that AS in this case turns out to be double integral over d norm of phi u cross phi v du dv. Okay. The analysis is exactly analogous. What you have to do is you have to linearize phi u v plus dv. Well, what you will be using is, for example, phi u v plus dv. Once you look at, you will say that this is approximately equal to phi u v plus phi v at u v then dv. Okay. Go on doing this for all the coordinates, then do exactly what I have done for the case when the surface is a graph. That is, you find P1, P2, P3, P4, find their lengths, and then apply the fact that norm of the cross product of the two adjacent vectors gives you the area of the rectangle. And in that case, what it turns out to be is norm of phi u cross phi v. And then to check, I can give it as an exercise that if you assume your phi xy to be equals to x, y, fxy. Suppose this is your phi, then show that norm phi x cross phi y is nothing but norm of the vector minus fx minus fy 1. Just show this as an exercise. That will show that the previous case, whatever I have done, has been generalized in the next case. Now, the next thing what I want to do is, applying this, I want to find the area of a given surface. Okay. So, let us look at the sphere again. So, let us say S equals to, so I want to calculate the surface area of the sphere of radius r. Then I know that the parametric representation of the sphere is given by whatever is written here, r sin u cos v, r sin u sin v, r cos u, where u varies between 0 to pi and v varies from 0 to 2 pi. I want to calculate the surface area of this sphere. So for that, what I need to calculate first is, what is phi u? Well, that is easily calculated. It is r cos u cos v, then r cos u sin v, then minus r sin u, that is phi u. Then I want to calculate what is phi v, that is minus r sin u sin v, r sin u cos v, then 0. Okay, and now I have to calculate phi u cross phi v. So for that, again I write down the determinant, that is I j k then minus r sin u sin v, r sin u cos v, then 0. Let us see what it turns out to be. So what I get out of this, let me write it down. I get r cos u sin v times 0, which is 0. Then the next component is r square sin square u cos v. That is the first one. Now with the j, what I get is, it's r square sin square u sin v. Okay. Then comes the k component, which I am going to write in the next line. K component gives me r square sin u cosine u, then cosine square v plus r square sin u cosine u sin square v. Okay. Now this last component, I can take this cosine square sin u cosine u r square to be common. Then what I am left with is sin square v and cos square v, which is 1. So the final result then would be r square sin u cosine u, that I will write down here. So this is r square sin u cosine u. Okay. Now I have to calculate the norm of this vector, that is the sum of the squares of this, and then I have to take the square root. Now once I do this, so norm of phi u cross phi v, if I look at, what do I get? So this is then equals to square root of, I first get r to the power 4, because everything is getting squared up. Then I have sin to the power 4u cos square v plus sin to the power 4u sin square v, that would produce sin to the power 4 u. And then the next thing is sin square u cosine square u. Okay. If I take sin square common, then I get 1. So the end result is actually equal to r square sin u. Okay. So it does not depend on v. So I have found out what is ds. Now I have to integrate it. So total area AS then is integral from 0 to pi, that is the variation of u, then 0 to 2 pi r square sine u, that is the area of the infinitesimally small rectangle which I have found and called ds. So this is ds, and then I am summing them up, so it is du dv. Okay. Now dv has nothing to do with the integrand, so it is just 2 pi r square, then integral 0 to pi sine u du. Okay. So that means it is 2 pi r square. Since I am going to get cos u, that is again going to produce a 2. So the final answer is 4 pi r square, which we already know. So by this method also we can find the surface area of a sphere. Now after this I am going to define surface integral of functions. So suppose S is a surface, let us say it is given by the parametric representation phi. So phi is a map from R2 to R3, okay, and phi of the domain of phi, which is I am calling R2, it might be some subset of R2 also, I do not care, this is my S, it is a surface. And suppose f is a function from the surface to the real line. Assume that f is continuous. Okay. Then I want to talk about the integral of this function over the surface S. So how do I define this? Well, integral over S f d sigma, that is the notation for the surface integral. I will tell you what exactly it means. Well, it is given by a double integral. Its meaning is the double integral over domain of phi f of phi uv, then the area of the infinitesimal small rectangle, that is phi u cross phi v, then du dv. Okay. This is what I mean by the integral of a function over a surface. So what you do is, given the function f, if the surface has the parametric representation phi, look at the function f compose phi. Now that is a function of two variables, that is the two parameters which I am using to define the surface. Then multiply with it the surface area of this infinitesimally small rectangle, that is ds, whose expression we have found out. It is the norm of the vector phi u cross product phi v. You get a number. Then look at du dv and do the double integration. That gives you the surface integral of the function over that surface. Now to exhibit this, I will look at an example of a particular function and a particular surface, and I will try to integrate the function over the surface. So in the example, let me look at the upper hemisphere of the sphere, that is z equals to a square minus x square minus y square whole to the power half, and z is bigger than or equal to 0, a belonging to R, a strictly bigger than 0. That is, what I have done is, my surface is the upper hemisphere of a sphere of radius a, where a is obviously positive, and I want to evaluate this integral, that integral over S d sigma by x square plus y square plus z plus a whole square. Okay. So this is the integrand is the function, and I want to integrate the function over this sphere. Okay. Now to evaluate this integral, I will use the parametric representation, that is x equals to a sin u cos v, y equals to a sin u sin v, z equals to a cos u. In that case, I know the area element ds, that turns out to be a square sin u. Okay. Then the double integral is, first the variation of u, since I am looking at the upper hemisphere, u varies from 0 to pi, v varies from 0 to 2 pi certainly. I get a square sin u du dv, that divided by square root of a square sin square u cos square v plus a square sin square u sin square v plus a cos u plus a whole square. That is 0 to pi, from 0 to 2 pi, a square sin u du dv, that remains. Now I concentrate on the denominator. If I add the first two terms, I get a square sin square u. Then from the third term, I get another a square cosine square u plus twice a square cosine u plus a square. Adding the first two terms again, I get a square. Anyway, there is another a square, so I get twice a square. So finally what I get is 0 to pi, 0 to 2 pi, a square sin u du dv divided by square root of twice a square plus twice a square cosine u. This, if I use the formula of cosine of u by 2, I get the following: square root of twice a square into 2 cosine square u by 2. Okay, this is then 0 to pi, sorry, it is 0 to pi by 2, because variation of u is from pi by 2. What I get is a square sin u du dv divided by twice a cosine u by 2, that then is equal to 0 to pi by 2, 0 to 2 pi, a sin u by 2, because sin u I can write as twice sin u by 2 cosine u by 2. So cosine u by 2 cancels, 2 also cancels, 1 a cancels, I get du dv. Now there is no v in the integrand, so I just get 2 pi, then 0 to pi by 2. A also I can take out, it has nothing to do with the integral, it is just sin u by 2 du, which now one can easily calculate, because the integration of sine and such things we can do. So this is how one does the integration. So I will repeat once again how to integrate a function over a surface. If you have a parametric representation of the surface, the first thing would be to find the area element, that is norm of the vector phi u cross phi v. That has to go with the du dv, where u and v's are parameters. Then what is your integrand? Your integrand is f of phi u v. Then calculate the variation of the limits of u and v, put those limits in the integral, write down the function f of phi u v, multiply it with the area element, that is norm of phi u cross phi v du dv. Calculate this double integral, that is the integral of the function over the surface.